Welcome back, everyone. Every day we like to check in and see how our attendees and speakers are doing. So let us know your thoughts and questions in the DSS Slack channel or on social media. Tag us and share your biggest takeaway of the day. You can also tweet straight from the event console, and our event hashtags will be included automatically. Our next speaker is Dominick Rocco. He's a data scientist at phData and will be talking about MLOps in practice, experiment tracking, and hyperparameter tuning. Welcome, Dominick. Take it away.
Hi, I'm here to talk about how to put MLOps into practice. Specifically, I'm going to talk about integrating machine learning operations into data science workflows through experiment tracking, and I'm going to talk about that in the context of hyperparameter tuning. So I will start by defining machine learning operations, what it is, what it means, and why it's important. I'll move on to talk about experiment tracking within machine learning operations and how to make research reproducible. Then I'm going to talk about a specific library called MLflow and how it helps us track experiments. And then I'll take MLflow and I'll show how to integrate it into complex data science workflows like hyperparameter optimization. So machine learning operations, or MLOps. The reality is that machine learning models are software. And creating great software requires great care. So MLOps is to machine learning as DevOps is to software. In the ideal world, the machine learning model lifecycle looks something like this. So we start with data discovery, where we gather our data, we explore what's going on in the data and create features, and really try to understand the business case. When we have that, we train models. We run experiments to find the best model, and we validate our hypotheses for modeling. When we have a model we like, we move on to deployment. So this means serving up the inferences or predictions of that model and integrating it into our systems. And once we've done that, we need to be monitoring, which means logging the behavior of our models, visualizing what's going on, and alerting when there are errors. Now, in reality, this tends to go very wrong. We've all seen this many times. A data scientist pulls some data down to their laptop, and they create this series of Jupyter notebooks to do different functions. They might do some filtering of the data and then send that over and do another notebook with some feature exploration and analysis exploratory. Then they learn some things, they do some more filtering, and now you've got who knows what data set. And then we use a data set to make some models, and we like them, so we throw them over the fence to some engineers. And the engineer receives a stack of notebooks and some data that they don't know where it came from, and confusion ensues. And the engineers struggle to reproduce results, and the deployment ultimately takes several months. There's a lot of consequences of this pattern. You might lose the original training set because it got deleted, or you might lose the source code for training. As I mentioned, the deployment can take a lot longer. Maybe you get to production and the accuracy of the model doesn't match what you saw in the lab, or the performance degrades over time and you're unable to train new models. And most significantly, the proposed business value that was uncovered by data science might never be realized. So when we get to MLOps, we have some core principles, and this is really an interplay between data science, machine learning engineering, and operations. It starts with data science. When we're exploring and creating models, we need to do reproducible research. That means we're always preparing for a transfer to engineering. It means we're preserving artifacts to do further research later, and we're allowing for retraining if needed. On the engineering side, when we deploy, we want to streamline that process, and we want to use repeatable architectures to get there, deploy continuously, and automate model retraining. And finally, once we're operating, we need to be excellent. We're monitoring for drift, alerting on failures, and being prepared to roll back. So for data scientists, the important thing to think about is experiment tracking. This is the foundation of reproducible research, and it gets us ready for streamlined deployments later. So when I talk about tracking, there's 4 key elements that come to mind. We need to be tracking our software, which means all custom code is in version control, and we're keeping track of our external dependencies. We need to track our data, which means making copies or snapshots of data. We need to track metrics, which means the input parameters as well as the performance metrics of our training jobs. And we need to track the models themselves, which would commonly be serialized model artifacts, so that we can compare and deploy later. And if we track these things, our experiments will be reproducible and results will be available for study at any point. So with software, this lets us iterate and refine and gets us ready to transfer things to engineering teams. So we always have to be thinking about keeping our custom code in version control throughout the whole development process and making sure that our environments are understood and tracked. So if you're using Python, for instance, and you have a requirements.txt, or if you're running out of a Docker container and you have a Docker file, you want to keep those things in version control too, so that when an engineer needs to have an environment, or another data scientist needs an environment later, they're ready to run this code. Retaining copies of our data lets us ask follow-up questions and retrain models. Ideally, you take snapshots of data. So that's not the whole data set, but we keep track of what's changing so we don't have to duplicate the data over and over again. And different data stores let you do that. It's also important to set appropriate retention policies so that we're cleaning up our data when necessary. If a model doesn't go to production, we don't need to keep that data around forever. For metrics, the real key here is to get everything to go to a common location so that we can make comparisons and optimize as we run more and more experiments. So we want to log all of the input parameters to our training jobs so that we know how we configured things. And we want to log the performance metrics for analysis and comparison. Finally, we want to store or track our models. So we're going to output serialized versions of our models. Most libraries have a recommended way to do this. And we're going to track the dependencies necessary so that we can load those models later. Now, all of that sounds like a lot of work. And the good news is that there are libraries like MLflow that make this straightforward for data scientists to integrate into their workflows. MLflow is an open source platform for the machine learning lifecycle. It lets us track our experiments with simple API calls, and it supports all common machine learning languages and frameworks. MLflow helps us analyze our results with a graphical user interface, as well as an API that lets us go through the history of results. And you can also search into previous results. And finally, MLflow helps us deploy our models. There's a toolkit to track deployments using Docker or Conda. And this lets us trace our workflows all the way back to model creation. Now, tracking in MLflow is simple. There are API functions for logging metrics or parameters, which are just key value pairs. So you have a value, which is the metric, and then it has a name, which is the string or the key. You call a function to do the logging. It automatically integrates with Git to capture the Git revision that you're currently running your experiment under. And it tracks environments too. It actually integrates with Conda or Docker to set up the environments in which experiments are run. So I'm going to do a quick little demo of what you see in the MLflow GUI or graphical user interface. So this is the homepage. I'm running inside of Databricks here where MLflow is built in. So every Databricks notebook has an MLflow experiment tied to it. And so this is the name of the notebook I was running in Databricks. You can see down here all of the history of experiment runs that I have launched. And I can see the metrics that I logged here in this table. So it shows me the parameters that were input to the jobs and then the performance metrics that came out. If I click on one of those I'll point out one more thing before I move on. So this is also searchable. So a user can type in some search parameters here and select runs that they want to look at more closely. Now, this is a particular run where I can see the listing of all the parameters that I've talked about. And I can see the metrics that I've recorded. And also the artifacts associated with that. So here I'm training models using LightGBM for gradient boosting. So the serialized model is right here. That's automatic and built into MLflow. And it has also captured feature importance so I can start to interpret what's going on with my model. Now, I've showed you that MLflow has a lot of features for tracking, and now what I want to show is that it doesn't take a lot to integrate this for a data scientist. So this is a block of code that I use for the analysis that was shown previously. And it's I don't want to go through this code line by line, but I do want to use it as a prop to show just how little of it is related to MLflow. So in this block of code, I fit a model, I do k-fold cross-validation, and I measure test metrics. But only 3 lines of this are related to MLflow. I have 1 line to register an experiment and start tracking. I have another line that enables auto logging for LightGBM, which enables the capture of the parameters, as well as the artifacts, the feature importance, and the model artifact itself. And finally, there's 1 line below to record metrics. So I have a Python dictionary of metrics, and I make 1 function call to ship all of those metrics off and be logged. So ultimately, in summary, I believe that strong MLOps is key for project success in data science and machine learning engineering. It starts in the data science workflows, and all data scientists should be thinking about experiment tracking so that they can do reproducible research. And MLflow is a library that makes tracking easy, and I'd encourage any data scientist to give it a try. If you want to learn more, we have an upcoming webinar on this topic. We'll share out the links in Slack, and we hope that you join us. Thank you.
Thank you, Dominic. That was a great presentation. We have now time for a few questions that came through. And the first question is, does the crisis you describe make a case for operational roles like project and product managers who act as middleware between the data science team and the engineering team? These roles will be data science literate, but focused on project completion to address what you highlighted. Do these roles exist currently?
So I think that these roles exist, and there are, managers and project managers involved in data science projects. And whenever there are, they should be driving reproducibility concerns and raising those from the beginning of a project. But really, it's data scientists who need to get invested in using technology such as MLflow. While it may deliver short-term results to ignore reproducibility, because you might get things done a little bit quicker by just banging it out, in the long term, projects will fail to deliver success and business value if you don't do the tracking. So I think that data scientists are the ones who need to stay up on the technology to get this done. And product managers can't really force specific technologies so much.
Great answer. Thanks, Dominic. Another question that came in is, how different is MLflow from other ML platforms like Azure ML?
Sure. Azure ML and the other sort of auto ML tools are really more involved in creating the models. They'll do the feature engineering and they'll train the models and do model selection or optimization. MLflow doesn't do that actual science work or data manipulation. It's really just a bystander to help you track the work you do. So when you use MLflow, you can use whatever tools you want, and you're really free to innovate and drive the process. MLflow just tracks what you're doing and aids in the operational aspects.
Thanks for answering that question. Another one is, what is the most important first step a data scientist can make to improve MLOps?
The most important thing is to always leave breadcrumbs or a paper trail for yourself and for your team. You want to make sure that you're documenting what steps you're taking from the beginning, and always thinking about, 3 months from now, how am I going to reproduce what I did? And by applying that mindset, you'll start to use tools like MLflow to make it easier for you to track what you're doing.
Great, thanks. Another one is, how do you see machine learning operations changing in the next few years?
I think in the next few years, the biggest change is just that it's going to be talked about a lot more and there's going to be more demand. Data science is in a phase now where it really needs to grow up. A few years ago, data science teams could get by just creating PowerPoint presentations that look really good and showing the results and promising business values. But in the next few years, data science projects and machine learning applications are really going to have to deliver business value. And if teams are deploying broken workflows and broken applications because they don't have good reproducibility, then they're not going to deliver business value. Their applications are going to fall down, and leadership is going to get frustrated. So that's going to create a demand for just more engineering and operations and really up the game in terms of excellence.
Great answer. Thank you, Dominic. The final question before we go into the break is, how can you compare MLflow to SageMaker?
Sure. I mean, SageMaker is a lot of things. SageMaker includes some of those auto ML tools that I was talking about before. It also includes some tracking. And it's really a whole ecosystem, and tracking is one part of that. So I think SageMaker has similar tools for logging results, and it has a dashboard that's similar. I think that one piece, the tracking part of SageMaker, is a competitor to MLflow. SageMaker also has tools for deployments where, once you train a model, you can flip it over and deploy it. So a lot of the concepts there are the same. At the same time, SageMaker is a much bigger umbrella, and part of SageMaker is actually to do some of that auto ML and the feature engineering and model development in addition. Again, the biggest takeaway from my talk is the principles and the mindset of tracking and being ready for deployment.
Awesome. Thank you so much for being here, Dominic, and answering all these questions. I'll put the others in Slack and tag you so you can keep the conversation going there. Thank you very much.
Great.
We now
Thank you.
have a 15-minute sponsored. Thank you. We now have a 15-minute sponsored break. Take some time to check out our awesome virtual sponsor booth. They have creatively adapted and provided a lot of great takeaways. You can enter all booths via the virtual lobby. Everyone who visits the booth is entered into a raffle for 25 pairs of DSS socks that I actually really like. So make sure to step by. And we will be back at 2:25 Eastern for an exciting talk about automated content marketing messages. Enjoy your break and see you all in a bit.